Imagine you are testing a login page. Would you test every possible username and password? That could take years. So, how do testers choose the right test cases? That's exactly what you'll learn today. What is a test case? A test case is a detailed document that describes how to test a specific feature of a software application. It tells the tester what should be tested, what data should be entered, what conditions must exist before testing, what steps should be performed, what result is expected, whether the test passed or failed. According to IEEE definition, a test case is a set of test inputs, execution conditions, and expected results developed for particular testing objective. In simple words, a test case is like a recipe for testing software. It tells the tester exactly what to do and what result should happen. Imagine you are testing a vending machine. Test case: input, insert 100 rupees and press Coke. Expected result: Coke is dispensed. Remaining balance is returned. If that happens, test passed. Otherwise, test failed. Software testing works exactly the same way. Let's use a login page. Username admin, password admin123, right? Every test case should have a test case ID, right? You can give any number for this, right? T, C, D, 001, 002, likewise, right? The next column, test scenario. According to this, we can test inputs with valid and invalid things. So, we put them into this section like this, right? The next column is preconditions. Preconditions in test cases are the required starting conditions system states or preparatory actions that must be met before a test can run. They ensure the environment is correctly set up so that tests are reliable, reproducible, and do not fail due to missing data or improper configuration. This is the example for preconditions. The next column is test steps. Test steps in a test case are the chronological, sequential actions a tester follows to validate a specific software feature. They translate the requirements into a repeatable workflow and are typically structured with the following key components. First one, actionable verbs. Start each step with clear instructions like click, enter, navigate, select. The second one is specific. Test data reference exact input values, credentials or items rather than generic placeholder. Example like enter john@joe.com, not enter valid email. The next one, sequential ordering. Break down process into atomic steps rather than combining multiple tasks into a single step. The last point is expected results. State exactly how the system should respond after each individual action, allowing the tester to catch failures early. We normally write these things like this, right? The next column is test data. Test data in test cases refers to the specific input values, configurations, and variables used to execute a test and verify how the software behaves. It acts as the ingredients required to follow the step-by-step test script and helps determine if the application meets its requirements. Test cases rely on several distinct types of test data to thoroughly check an application. Valid data. It means correct and acceptable inputs. Example, a valid email address that tests standard functionalities and confirm the system produces the expected results. Invalid data. Incorrect or improperly formatted inputs. Example, entering ABC in a phone number field. Used to verify the system's error handling and validation capabilities. The next one, boundary data. Input values at the extreme ends of allowed limits. Example, minimum and maximum character counts. To test edge cases, test edge cases. The next one, empty or missing data. Leaving required input fields blank to ensure the system properly identifies missing mandatory information and displays appropriate error messages. The next one, huge or large data. Massive volumes of data used in performance and stress testing to evaluate how well the system scales and whether it handles heavy loads without crashing. See, we can include test data like this. This is the username, this is the password. The next column is expected result. Under that, we give the correct outcome if the application behaves as intended. We can give example like this. The next column is actual result. It means the result observed after executing the test. The next one, status. It indicates whether the test passed or failed. We can give pass or fail, not both, right? Test case formula. Every test case should answer these questions. What are we testing? We can tell test scenario. What should be true before testing? It can be predictions, right? What steps should be followed? Test steps. What input will be used? test data. What should happen? Expected result. What actually happened? Actual result. Did it pass or fail? Status, right? Think of a test case as a cooking recipe. A recipe tells you the ingredients, the preparation steps, and what the finished dish should look like. Similarly, a test case tells the tester what inputs to use, what steps to follow, and what result the software should produce. If the software produces the expected result, the test passes. Otherwise, it fails. The next topic is good test cases. What makes a good test case? A good test case is one that is clear, reliable, practical, and capable of finding defects in the software. We can give the simple definition like this. A good test case is one that has a high chance of finding bugs while being easy to understand, execute, and repeat. And this first point is have a high probability of finding a new defect. What does it mean? A good test case should be designed to discover defects that have not yet been found. The objective is not just to confirm that the software works, but to uncover hidden problems. For an example, suppose a login system accepts password between 8 and 20 characters. A weak test case, password is equal to password 123. This simply confirms that the feature works. A stronger test case, password with 7 characters, password with 21 characters, empty password, password containing only spaces, password containing special characters. These inputs are much more likely to expose defects. What is the simple idea of this? Good test cases test both valid and invalid conditions. The second point is unambiguous tangible result that can be inspected. What does it mean? The expected result must be clear and measurable. Anyone executing the test should know exactly what outcome to expect. For a banked example, expected result is login works correctly. This is vague. Good example, expected result, user is redirected to the dashboard. Welcome message displays the username. Login occurs within 2 seconds. These outcomes are specific and can easily be verified. What is the simple idea of this? Expected results should be objective, not open to interpretation. The third point is repeatable and predictable. What does it mean? Running the same test under the same conditions should always produce the same result. A test should not pass once and fail another time without changes to the software or environment. For an example, test case, we can get username as admin, password as admin123, right? If executed today, tomorrow, or next weak in the same environment, the expected outcome should remain the same. What is the simple idea of this? Consistent inputs should lead to consistent results. The fourth one, traceable to requirements of design documents. What does it mean? Every test case should correspond to a documented requirement of design specification. This ensures that every system requirement has been tested. For an example, your requirement is users must be able to reset forgotten passwords. What about related test case? Click forget password, enter a registered email address, verify that a password reset email is sent. This demonstrates clear traceability. What is the simple idea of this? Every requirement should have one or more associated test cases. The fifth one, execution and tracking can be automated. What does it mean? Good test cases are structured so they can be executed manually or automated using testing tools. Automation saves time, especially for repetitive tests. For an example, manual test, open browser, enter username, enter password, click login, right? This sequence can also be automated using tools such as Selenium. What is the simple idea of this? Well-structured test cases are automation friendly. The sixth point is do not mislead. A test case should be easy to understand and should not confuse the tester. The instructions should be precise and complete. For a poor example, the steps should be enter data, what data, where should it be entered. For a better examples, your steps should be enter admin in the username field, enter admin123 in the password field, click the login button. There is no ambiguity. What is the simple idea of this? Clear instructions reduce execution errors. The last point is feasible. What does it mean? A good test case should be realistic and executable using the available resources. For a good example, test login with Google Chrome, Firefox, Microsoft Edge. These browsers are commonly used and available. For poor example, test login on 500 different browser versions. This is generally impractical and not cost effective. What is the simple idea of this? Test cases should be achievable within the project's time, budget, and resource constraints. The next topic is test case design technique. The first one, black box testing or functional testing. Under this, we have five types to learn. What are they? They are equivalence partitioning, boundary value analysis, cause effect graphing, behavioral testing, and random testing. Did you know that in black box testing, we don't look at the source code, but we can still design powerful test cases? In this lesson, I'll explain the three major approaches used in black box testing with simple examples that you will never forget. Let's get started. Before we discuss the three approaches, let's quickly remember what black box testing is. In black box testing, the tester does not know or inspect the internal source code instead. Source code, right? Instead, the tester focuses on what inputs are given, what outputs are produced, whether the software behaves according to the requirements. Think of it like using a vending machine. You don't know what's happening inside the machine. You simply insert money and press the button and check whether you receive the correct item. The first approach is analysis of the input and output domain. What does it mean? The first approach is called analysis of the input or output domain. Here we study all possible inputs and outputs of the software. Since testing every possible input is impossible, we divide the inputs into logical groups and also called partitions or interesting subsets. Then, instead of testing every value, we select representative values from each group. This is the foundation for techniques such as equivalence partitioning and boundary value analysis. For an example, imagine an age field that accepts values from 18 to 60. What are the possible inputs? -50, 0, 10, 18, 25, 45, 60, 61, 100. Instead of testing every number, we create partitions. What are the invalid partitions? Less than 80. Examples 10, 15, 0. What are the valid partitions? Between 18 and 60. For examples 18, 30, 45 and 60. Invalid partition greater than 60. For examples 61, 75, 100. We only choose a few representative values from each partition. This saves time while still providing good test coverage. The next approach is analysis of observable black box behavior. What does it mean? This studies how the software behaves rather than simply what values it accepts. We observe the different states, screens, or actions the user can perform and the transitions between them. This often produces a model that looks similar to a flow graph or a state transition diagram. Although we are not examining the source code, we still create a logical model of the application's behavior. Consider an ATM. Possible states are: first, we should start, then insert your card and enter PIN and select transaction and withdraw cash and finish it. We test the different paths through these states. Examples: if we insert correct PIN, cash is dispensed. If we insert incorrect PIN, error message appears. What about 3 incorrect PIN attempts? Card is blocked. If user presses cancel, transaction ends. Notice that we are testing the application's behavior, not its internal code. Think about an online shopping website. We move on to the home page and search product, add to cart, checkout, payment and order confirmation. We verify that each transaction works correctly. The last approach is other black box techniques. This category includes several additional black box testing techniques that don't rely on input partitioning or behavioral models. Let's look at 3 common examples. The first one, risk-based testing. It prioritizes testing according to the likelihood and impact of features. Features with higher business risk receive more attentions. What are the examples for banking application? And what are the high-risk features? Money transfers, online payments, login authentication. What are the lower-risk features? Challenging the application's theme color. Naturally, testers spend more time validating the high-risk features. The next one, random testing. In random testing, inputs are selected randomly instead of following a predefined pattern. The objective is to discover unexpected defects. Example, testing a username field with values such as these things, right? Unexpected combinations sometimes reveal defects that structured testing might miss. The next one is stress testing. Stress testing checks how the system behaves under extreme conditions. The objective is to determine whether the software remains stable or fails gracefully. Imagine an online ticket booking website. Normally, 1,000 users can access it without any issues, right? But what about stress testing? 1 lakh users access the website simultaneously. We observe whether the application crashes, it slows down significantly, users receive appropriate error messages, the system recovers after the heavy load. Stress testing focuses on the software's behavior under conditions beyond its expected capacity. Let's learn one of the most important black box test design techniques. First one, equivalence partitioning, also known as equivalence class partitioning. This technique is frequently tested in exams and widely used in the software industry. Equivalence partitioning is a black box design technique that divides the input data into logical groups called equivalence classes, where all values in the same group are expected to behave similarly. Instead of testing every value, we select one representative value from each class to create test cases. Imagine a classroom with 100 students. Instead of interviewing every student individually, you divide them into groups based on similar characteristics, and you interview just one student from each group because you expect everyone in that group to give similar answers. Equivalence partitioning works exactly the same way. Instead of testing every input value, we divide the inputs into logical groups and test one representative value from each group. Without equivalence partitioning, suppose an application accepts values from 1 to 100. You might think you need to test 1 to 100 values. That's 100 different test cases. But with equivalence partitioning, we only create a few carefully chosen test cases. What are the advantages of this? It reduces the number of test cases and saves testing time, saves effort and cost, maintains good test coverage, and makes testing more efficient. What are the steps of equivalence partitioning? Let's learn the process step by step. The first step is identify the input range or condition. First, identify what the system accepts. For an example, the system accepts an integer from 1 to 100. This becomes our testing condition. The second step, divide the input into equivalence classes. Now, divide the inputs into logical groups. For these examples, we have 3 equivalence classes. Valid equivalence class 1 to 100. Every value here is expected to be accepted. Examples, we can test 1, 25, 50, 75 and 100. The second one, invalid equivalence class 1. Values less than 1. For examples, we can test 0, -1, -50. They should be rejected. The next class is invalid equivalence class 2. Values greater than 100. We can test 101, 150, 1000. They should also be rejected. Step 3. Select one test case from each class. Now, we don't need hundreds of test cases. We simply choose one representative value from each class. For example, valid class choose 50. It is expected result is accepted. The next one, invalid class for below range. Choose 0. Expected result is an error message. The next one, invalid class for the above range. Choose 101. Expected result is an error message. Instead of testing every possible value, we only test 3 representative values. This diagram clearly shows the 3 equivalence classes. We can write test cases as this, right? For equivalence classes partitioning. Imagine an online examination system. Students must enter marks between 0 and 100. What are the possible equivalence classes are? First one, valid class 0 to 100. If our representative value is equal to 80, it is accepted. The next, invalid class, we give below 0 numbers. Representative value -5 is rejected. The next one, invalid class above 100. Representative value is 110. Rejected. Again, only 3 test cases are needed. For another example, age validation. What are the requirements? Age must be between 18 and 60. What are the equivalent classes? Valid 18 to 60. Representative value is 30. It is valid. The next, invalid classes. Invalid class below 80. Representative value is 16. Invalid above 60. Representative value 65. Only 3 tests are sufficient. Many beginners think if the valid range is 1 to 100, I should test every number. That's incorrect. Equivalence partitioning assumes that all values in the same equivalence class behave similarly. Therefore, testing one representative value from each class is generally enough. What are the advantages of equivalence partitioning? It saves testing time, reduces the number of test cases, reduces testing costs, improves testing efficiency, provides good functional test coverage, easy to understand and apply. What are the limitations? It assumes all values within a class behave the same, which may not always be true. It does not specifically target errors at the edges of input ranges. That's why equivalence partitioning is often combined with another technique called boundary value analysis, which focuses on testing value at the boundaries. Let's learn another important black box test design technique called boundary value analysis, or simply we can say BVA. In fact, boundary value analysis is often used together with equivalence partitioning because they complement each other. What is boundary value analysis? Boundary value analysis is a black box or specification based test design technique that focuses on testing values at the boundaries of an input range, as well as the values just below and just above these boundaries. Sorry, it's not these, it should be those, right? Sorry, my fault. Think of a bridge. The strongest part of the bridge is usually the middle, but the points where the bridge starts and ends are more likely to develop problems. Software behaves in a similar way. Most defects occur at the edges of valid input ranges rather than in the middle. That's why we pay special attention to the boundary values. Why do we use boundary value analysis? Suppose a system accepts numbers from 1 to 100. Will the system fail when the user enters 50? Probably not. But what about these values? These values are much more likely to reveal defects. That's the idea behind boundary value analysis. Relationship between EP and BVA. EP means equivalence partitioning. This is boundary value analysis, right? You often ask which comes first, equivalence partitioning or boundary value analysis. The answer is first use equivalence partitioning to divide the input values into valid and invalid classes. Then apply boundary value analysis to test the values around the boundaries of those classes. Think of it this way. Equivalence partitioning asks what are the different groups of inputs. Boundary value asks what happens at the edges of those groups. Example 1. Suppose the system accepts numbers from 1 to 10. The valid range is this, 1 to 10, right? The boundaries are, what is the lower boundary? 1, right? The upper bound is 10. Boundary value analysis tells us to test these things 0, 1, 2 and 9, 10, 11, right? Notice something interesting. We test 0, 1, 2, then 9, 10 and 11, right? Okay. We don't test every value. We only test the values around the boundaries. Why these values? First one, lower boundary. Boundary value is 1, right? Expected result is accepted, right? Then just below the lower boundary is 0. Expected result is rejected. Just above the lower boundary is, this 2. Expected result is accepted. Upper boundary is 10 and expected result is accepted. Just below the upper bound is 9. Accepted value is accepted, right? The just above the upper boundary is 11. Expected result is rejected. Notice that we didn't choose values like 5 or 7 because boundary value analysis focuses on the edges of the valid range. What are the steps of boundary value analysis? First step. Identify the valid input range like 1 to 100. The second step is identify boundaries. This is lower boundary. This is upper boundary. The third step is test the values. First, just below the lower boundary, at the lower boundary, just above the lower boundary, and just above the upper boundary, at the upper boundary, and just below the upper boundary. We can represent it like this, right? This is invalid input range. This is valid input range, right? You can see this is the lower boundary, and just above the lower boundary, just below the lower boundary, and this is upper boundary, and the above the upper boundary and the below the upper boundary, right? This is standard boundary value analysis pattern used in software testing. Imagine an ATM. Withdrawal amount must be between 500 rupee and 20,000 rupee. Boundary values come like this, right? Instead of testing hundreds of withdrawal amounts, we focus on the boundary values because they have the highest chance of exposing defects. Please find out difference between equivalence partitioning and boundary value analysis, right? Many students think if the range is 1 to 100, I should test 50. That is useful for equivalence partitioning. But BVA is different. Boundary value analysis focuses on the lower upper boundary and the values immediately below and above each boundary. The middle values are generally not the primary focus of BVA. What are the advantages of boundary value analysis? Find defects that commonly occurs at boundaries, reduces the number of test cases, improves test effectiveness, easy to understand and happy, works well with equivalence partitioning. Sorry, it should be easy to understand and apply. My mistake. What are the limitations? Best suited for input with clear numeric or ordered ranges. It does not test every possible value within the range. It may not detect defects unrelated to boundary conditions. Now let's move on to another important black box test design technique called decision table testing. Decision table testing is a technique used when the output of a system depends on multiple input conditions of business rule. In other words, when there are several conditions and each combination of those conditions can produce a different result. Decision table testing helps us organize and test them systematically. Decision table testing is also known as a cause-effect table. Why? Causes represent the input conditions. Effects represent the outputs or actions produced by the system. Simply remember, cause is equal to input and effect is equal to output. Why do we need decision tables? Imagine you are testing an online shopping website. Whether a customer receives free shipping doesn't depend on just one condition. It may depend on whether the customer is a premium member, whether the order value exceeds 1000 rupees, whether a promotional offer is active. Now we have multiple conditions working together. Testing each condition separately is not enough because the final result depends on their combination. That's exactly where decision table testing is used. It is focused on business rules. Decision table testing is mainly used to validate business logic or business rules. A business rule is simply a condition that determines how the system should behave. For example, a bank may have the following rules. Approve a loan only if customer's credit score is above 700. Customer has a stable income. If either condition is not satisfied, the loan is rejected. This is a business rule. Decision tables help us verify that every possible combination of these conditions works correctly. A decision table has 4 parts. The upper part contains the conditions. See, the lower part contains the actions or expected results. Each column represents one possible combination of inputs. Suppose a user can log in only when username is correct and password is correct. There are 2 input conditions. Let's create a decision table. Let's understand each rule. I already created. If the username and password are correct, the result should be given as login is successful. You can see it, right? If the username is correct and the password is incorrect, the result should be given as invalid password. See? If the username is incorrect and the password is correct, the result should be given as invalid username. You can see this, right? If the username and password are incorrect, the result should be given as login failed, right? This single table covers every possible combination. The next topic is number of possible combinations. A very common exam question is, How do we calculate the number of possible combinations? The formula is equal to 2 to the power n, where n is equal to number of input conditions. Each condition has only two possible values, yes and no, or true and false, right? Therefore, every new condition doubles the number of combinations. If we have two conditions, username correct, password correct, number of combinations we can calculate using this. 2 to the power 2 is equal to 4. Exactly the 4 combinations we listed in our table. Instead of guessing different situations, decision table testing guarantees that every possible combination is tested. What are the advantages of decision table testing? The first point is complete test coverage. According to this, decision tables ensure that every possible combination of condition is tested. This reduces the chance of missing an important test case. The next advantage is reduces rework. Since every combination is identified at the beginning, testers don't need to keep adding forgotten test cases later. This saves time and effort. The third advantage is handles complex business logic. Business applications often contain complicated rules. Decision tables convert those complicated rules into a simple table that's easy to understand. Examples include banking systems, insurance systems, payroll systems, airline booking systems, and e-commerce websites. The next advantage is easy to understand. The table format is very simple. Developers, testers, business analysts, and even clients can understand it easily. The next advantage is completeness property. This is one of the biggest advantages. Decision tables guarantee that every possible combination of conditions has been considered. This is called the completeness property. Nothing is accidentally left untested. When should we use decision table testing? Use decision table testing when multiple input conditions affect one result, the software contains business rules, several combinations of inputs must be validated, you need complete test coverage. When shouldn't we use it? Decision tables are not ideal when there is only one simple input, the system doesn't involve combinations of conditions, too many conditions exist because the table becomes extremely large. For an example, 10 input conditions, number of combinations are equal to 2 to the power 10. It's near to 1024 combinations. Testing every combination may become impractical. Now, let's understand two important terms you will often see in software testing: cause and effect. What is a cause? A cause is an input condition or event that makes something happen in the system. Simply put, like this. For example, Suppose a user wants to log into an application. Possible causes are username is correct, password is correct, account is active. There are all input conditions. What's an effect? An effect is the output, action, or final state that results from one or more causes. Simply remember, effect is equal to output or result. Examples: login successful, login failed, account locked, error message displayed. These are all effects. Simple example: imagine a login page. What are the causes? Username and the password are correct. What are the effects? User logs into the system, error message appears. Notice something important. One effect usually depends on multiple causes. For example, login success happens only when username is correct and password is correct. Let's move on. Cause-effect analysis. Instead of testing every possible situation randomly, we first identify all the causes and effects. Then we analyze how each combination of causes affects the system. Finally, we convert those combinations into a decision table from which we create test cases. That's why cause-effect analysis and decision table testing are closely related. Another concept you will hear is the fishbone diagram, also called the Ishikawa diagram. It was invented by Kaoru Ishikawa. It gets the name fishbone diagram because its structure looks like the skeleton of a fish. The head of the fish represents the problem, while each bone represents a possible category of causes. It is mainly used for root cause analysis, which means finding the real reason behind a problem. Instead of fixing symptoms, we identify the actual cause. Situation 1. Identify root causes. Suppose customers complain that the application is extremely slow. Instead of immediately changing the code, we investigate possible causes. Maybe it's database problem, server overload, network issue, poor SQL queries, memory leak, right? The fishbone diagram helps organize all these possible causes. Situation 2. Understand relationships. Sometimes many different factors affect one problem. Example: website crashes. Possible causes include high CPU usage, too many users, low memory, slow database, network failures. The fishbone diagram helps us see how all these factors relate to the final problem. Situation 3. Analyze existing problems. Suppose users cannot complete online payments. Instead of immediately fixing random parts of the system, we first analyze every possible cause. Once we identify the real cause, corrective action can be taken quickly. Benefits of fishbone diagram: helps find root causes. Instead of guessing we investigate systematically. The next benefit is easy to understand. The fishbone structure is simple. Everyone can participate. Developers, testers, managers, business analysts. The next benefit shows cause and effect relationships. It clearly connects possible causes to one final problem. The next one helps data collection. Once possible causes are identified, the team knows exactly what information needs to be collected. Example, if database performance is suspected, we collect query execution times, CPU usage, database logs. The next one improves process knowledge. The whole team learns how different part of the system affect one another. It should be different parts of the system. Sorry. Now let's move to another black box testing technique called error guessing. Unlike equivalence partitioning or boundary value analysis, error guessing has no mathematical formula. Instead, it depends entirely on the tester. Experience, knowledge, intuition. What is error guessing? Error guessing is a testing technique in which experienced testers predict where defects are most likely to occur. In other words, the tester asks, if I were this application, where would I probably... Example 1. Imagine you are testing a calculator. An experienced tester might immediately try divide by zero, very large numbers, negative values, decimal values, blank input. These aren't chosen randomly. They are chosen because similar defects have appeared in previous projects. Another example, testing a login page. Experienced testers often try empty username, empty password, both fields empty, very long password, SQL injection, special characters, spaces only. These scenarios come from experience. What are the characteristics of error guessing? The first one, based on experience. It usually performed by senior testers. Beginners often don't know where software commonly fails. Second one, done after format testing. Error guessing is usually performed after techniques like equivalence partitioning, boundary value analysis, decision table testing have already been completed. The next one, mainly used before release. Before releasing the application, experienced testers perform error guessing to discover defects that structured techniques may have missed. The next one is less reproducible. Since different testers have different experiences, they may guess different defects. Two testers may perform completely different tests. The next one, limited coverage. The next benefit, limited coverage. Coverage depends on experience, domain knowledge, available testing time. The next topic, checklist-based testing. Many organizations maintain checklists of common mistakes. Examples, divide by zero, empty input, invalid file type, large file upload, duplicate records, network interruption, browser refresh during payment. These checklists help testers remember common defect scenarios. Now, let's discuss another black box testing technique called random testing, also known as monkey testing. What is random testing? Random testing means providing random inputs to the software without following predefined test cases. The goal is to observe whether the application behaves correctly or crashes unexpectedly. Why is it called monkey testing? Imagine giving a keyboard to a monkey. The monkey presses random keys without following any rules. Surprisingly, this sometimes reveals hidden defects. That's why it's called monkey testing. When is random testing used? Random testing is useful when there isn't enough time to prepare detailed test cases. Quick reliability testing is needed. The team wants to discover unexpected defects. What are the characteristics? First one, random inputs. Inputs are selected randomly. These are the examples, right? The next one, finds unexpected defects, right? Some defects only appear when users enter strange or unexpected data. Random testing helps discover those situations. The next one, saved time. Preparing detailed test cases takes time. Random testing allows quick testing when deadlines are tight. The next one, test reliability. Random inputs help evaluate how stable the software remains under unusual conditions. What are the steps of random testing? First one, identify random inputs. Step 2, select random values from the input domain. Step 3, execute the tests. And step 4, compare the actual results with the expected behavior. Step 5, if a defect appears, record it, reproduce it, report it, fix it, and finally perform testing. Example, suppose you are testing a registration form. Instead of carefully entering valid data, you randomly type name like %%, age like -500, email like abc@gmail, phone number like abcdefgh. If the application crashes, you discovered a defect. Find out difference between random testing and error guessing, right? That brings us to the end of today's lesson on black box test design techniques. We covered equivalence partitioning, boundary value analysis, decision table testing, cause and effect concepts, and error guessing and random testing with practical examples. These techniques are essential for designing effective test cases and are commonly asked in exams as well as used in the software industry. In the next lesson, We'll continue exploring more software testing concepts with easy to understand explanations and real world examples. If you found this video helpful, don't forget to like, share and subscribe to support the channel. Thanks for watching and I'll see you in the next lesson. Bye bye.